Looking at the solutions for your NEET test file regarding those questions which belong to dual nature of radiation and matter. This question paper is a combination of extremely conceptual and extremely calculation intensive types and categories. So let's see how simple a job we can make of each of these questions. So let's begin with the first question from dual nature. It is to match the following type. In match the following, we need not go through each of these questions and try to match them. That would be stupidity in the exam hall. Instead, what we try is we shall go for the first question A and try to match that correctly. If frequency is increased, we know that stopping potential and maximum kinetic energy, both of them depends only on the frequency of the incident radiation. So if frequency is increased, then stopping potential increases and maximum kinetic energy also increases. So the right choices for A is P and R. Which of the following options have A matched with P and R? It is yes, option A and option C. Straight away, I can eliminate B and D. Now looking at A and C. You see, A is P and R. Here also A is P and R. B is QS. Here B is cleverly SQ. Just the priority, just these things, I would say. The order of options is changed, but nothing else much. But let's see D. D is PR. Here D is RP. Not any much difference. But yes, look at C. In the first option, A, C is matched with S, but in the third option, C is matched with Q. So if I just get hold of C, my question is done. C says if the distance between anode and cathode increases, then we look at choice S. Will stopping potential remain the same? Absolutely yes, because stopping potential depends only on the frequency and it doesn't depend on the distance between anode and cathode. We have hit the jackpot because C is correctly matched with S, straight away I can say that A is the right option. I did not go through B or D much. It is just solving just two questions and looking at the options. I can take I can take the maximum benefit of time over here. That is question number 98. Now question number 99. Work function of sodium is 2 eV, aluminium is 4.2 eV. Well, if work function, if I express in terms of cutoff frequency or threshold frequency, it is h nu naught. If threshold energy or work function is high, then cutoff frequency should also be high. So which of these has high threshold frequency? Aluminium has higher threshold energy, therefore it should have higher threshold frequency. So threshold frequency of sodium should be less than that of aluminium. So first choice is again correct. Going on to 100. If alpha, beta, and gamma rays is just light, alpha rays are helium nuclei, beta rays are electrons. They carry the same momentum, which will have the longest wavelength, de Broglie wavelength. De Broglie wavelength for light as well as matter is lambda equal to h by p. Since all the three have the same momentum, their wavelengths also will be the same. So all will have the same wavelength. Now moving on to question number 101. There are two charges, they have the same exact mass and they are accelerated through the same potential difference, but one has a charge of q whereas other has a charge of 2q. Which one will have a longer de Broglie wavelength? We know lambda is equal to h by square root of 2m qv. For both of these charges, 2m and v are same, right? So if charge is less, then lambda will be more. So longer wavelength will happen for whatever charge which has a less or least magnitude. Between A and B, which has least magnitude of charge is obviously A. So A will have a longer de Broglie wavelength. I can eliminate B and D because it says particle B has longer de Broglie wavelength. Now between A and C, how to make sense? Lambda is inversely proportional to P. So if P is less, then lambda is more. Particle A has a smaller momentum and hence longer de Broglie wavelength. So 101 correct option goes with C. This is how, reading the options carefully, we can arrive at the answer quickly. Question number 102. In a photoelectric experiment with light of wavelength lambda, fastest electron has speed v. If the exciting wavelength is changed to 3 lambda by 4, the speed of the emitted electron will become. Okay, so here we may need to work out something. So what we'll do is Einstein's photoelectric equation, hc by lambda is equal to 5 plus uh, half mv square. That is for the first electron. For the first electron, for the second electron, lambda has become 3 lambda by 4. So if I write it, 4 hc by 3 lambda should be equal to 5 plus half mv1 square. Okay. Now, uh, from these two equations, I am expected to solve for V1 in terms of only V. V1 in terms of only V. However hard I try, I cannot eliminate lambda from these. I can simply subtract them. I can remove phi, threshold function, but I cannot explicitly take or guess the form of V1 in form of V. I can't do that. Therefore, I can eliminate option A and B, which gives V1 in the form of V exactly. All I can do is I can try some sort of inequality. Okay, is it less than v times square root of 4 by 3, or is it greater than v times square root of 4 by 3? Is this lesser or is this greater? Well, so for that, we will try subtracting the equations, and then we will try to get the right form of the inequality. So what do we do here? We will say that when I subtract the two equations, I get, so if I subtract these two, okay, hc by lambda times, if I take it common, 4 by 3 minus 1 is equal to half m times v1 square minus v square. Okay, so from this, what do I get? I get 3, or I get hc by 3 lambda is equal to half m times v1 square minus v square. Okay, so what would be v1's half mv1 square in terms of half mv square? Half mv1 square has to be equal to hc by 3 lambda plus half mv square. So I have tried to look at v1 square in terms of v square, but how can I put it in terms of inequality? Okay, that is the problem here. So let's check. Well, for this, I can see that v1 square is definitely greater than v square. How many times v square? It should be greater. So I can say option should be D over here. But the detailed mathematical manipulations will take some time. So if you have to guess, you can guess option D. You can't work it out in a very limited time. Now going to 103. In 103, work function of a certain metal is so and so. Maximum kinetic energy of photoelectron of wavelength so is what? Okay. Maximum kinetic energy of photoelectrons emitted. How do I get that from work function and stuff? Well, Einstein's photoelectric equation, hc by lambda is equal to 5 plus max kinetic energy. Well, I will not use hc by lambda as such, okay, because they have given light of wavelength in angstroms. So I will use that form of 12,400 by lambda in angstroms form. And phi has to be converted into EVs. How do I do it? I know that 1 EV is 1.6 into 10 power minus 19 joules. So how much would be 3.31 into 10 power minus 19 joules? Well, if you do the math, it would be approximately 2 EV. Okay, so the threshold function is 2 EV, and the incident energy I can calculate by 12,400 by lambda in angstroms. I can get kinetic energy out, right? So I can eliminate two options actually. One is 248 EV and 2.07 EV because or 2.07 because I am subtracting 2 from something, right? So on the first side, you can eliminate that, but detailed mathematical calculation is necessary. That is question number 103. Now, question number 104. A and D are two metals with threshold frequencies 1.8 and 10 power 14 hertz, and the other one in hertz. Uh, they're asking which metal will emit photoelectrons. First, I will convert this EV into joules. How many joules? So again, one EV is 1.6 to 10 power minus 19 joules. 0.825 EV will be 1.6 into 0.825 into 10 power minus 19 joules. So the threshold function in terms of joules is this: 1.6 into 0.825 into 10 power minus 19. We will compare threshold function with the individual photons energies. What would be that? E equal to h nu. So I will multiply 6.6 into 10 power minus 34 with this, and 6.6 into 10 power minus 34 with this, and check whether are both of them greater than 5, any one of them less than 5. That will determine. So what is the condition? Condition is incident energy should be greater than 5. That is the condition for emission. I have got to know 5. I will calculate h nu and see which of these will be greater than the number given here that will emit the photon. That is question number 104. Now question 105. Number of photons incidents per square meter per second. Two formulas to be followed for 105. One is P equal to IA. The other formula is P is equal to NHC by lambda. Power is intensity into area. Here 1.388 into 10 power 3 watt per meter square is intensity. Intensity ka synonym is energy flux. Okay. So they have given intensity. So intensity of light has been given. What about area? Area has been given indirectly. Number of photons per square meter is what they are asking. So I can put area as 1 and intensity to be 1.388 into 10 power 3. I can find out the power. Whatever value I find out there, I can put over here so that I know H, I know C, lambda has been given in terms of 550. You need to convert it to SI because all options are in SI. So lambda has to be converted to nanometers. The only unknown will be N, where N is number of photons per second. That's it. As simple as this. Power is intensity into area. Power is also NHC by lambda. We feed the output of one formula to the input at the other. That is question 105. Question number 106. What would be the ideal approach for question 106? A difference between kinetic energies. This is slightly mathematical. We know that kinetic energy through Einstein's photoelectric equation is hc by lambda incident energy minus threshold. So kinetic energy of the first is equal to hc by lambda 1 minus phi, whereas kinetic energy in the second case 2 is hc by lambda 2 minus phi. They are asking what is the difference between these energies. So I need to simply subtract one from the other, then phi's will cancel and express hc by lambda 1 and hc by lambda 2 as much as possible in EVs, so that so here I don't use HC form. Instead, I will use 12,400 by lambda in angstroms. You do this, you'll get the difference in kinetic energies, delta kinetic energy in terms of all these numbers. So that is approach for question 106. Now question 107. Radiations of 2 photons energy twice and 10 times the work function of a metal are incident on a metal surface successively. What is the ratio of maximum velocities of photoelectrons emitted in the two cases? Okay. First one is radiations of, there are 2 photons. The first case is energy is twice the work function of the metal. For the first photon, energy is, incident energy is 2 phi, threshold is phi, plus half m v1 square. For the second photon, it is 10 times work function. So 10 phi incident equal to phi plus half m v2 square. So this much we can figure out. Now I need the ratio of V1 is to V2. I subtract. So 2 5 minus 5 would give you 5. 5 is half m V1 square, whereas 5 goes there. 9 5 equal to 5 half m V2 square. I divide them. 5 get cancelled. Half m get cancelled. And I need V1 by V2. That would be root. So it should be 1 is to 3. So 1 is to 3 would be the ratio of maximum speed of the electrons in the two cases, which would be B option. So this is also slightly mathematical. Now question number 108. Maximum wavelength of radiation that can produce a photoelectric effect. Wherever they say maximum wavelength, they are indicating the threshold wavelength. So 200 nanometer is the threshold wavelength. If they say minimum frequency, that would be threshold frequency. Whenever they say maximum wavelength, that is the threshold wavelength. Now, what is the maximum kinetic energy acquired by electron due to radiation of 100 nanometers? Again, every option is in EV. So what will I do? 12,400 by incident radiation wavelength, 100 nanometers. 100 nanometers is 1000 angstroms. That is equal to work function. How do I find work function? 12,400 by lambda in nanometers, which would be 2000. Okay. This plus half mv square. Remember, this one is what we are seeking, what we need, maximum kinetic energy. That is already in units of EVs because this is in EV, this is in EV. So I will simply subtract the two numbers. Whatever I get, that will be the answer. That is question number 10. Now, question number 109. A photosensitive surface is receiving the light of wavelength so at the rate of 10 power minus 8 joule per second. What is the number of photons received per second? Again, here, joule per second is nothing but energy per unit time, that is power. For 109, I can use P equal to N hc by lambda, where n is number of photons incident or received per second. P is already given 10 power minus 8 watts, and h value we know, Planck's constant they have also given, and c value they have also given, we also know that, and lambda is 5000 angstroms, and here everything is in SI. So we need to convert angstroms to meters and then do it. 1 angstrom is 10 power minus 10 meters. This will aid in the calculation. This is the approach for 109. Now 110, power is given, the number of photons is given. What radiation or to what spectrum does this belong to? Well, for this, again, I shall take the help of P equal to NHC by lambda, or P is equal to NH nu. But a spoiler alert, the thing is you need to know frequencies or the wavelengths of each of these rays, X-rays, UV rays, microwaves, and gamma rays. If you don't know the frequency or wavelengths, you cannot do this question. So first step is find out the frequency or find out the wavelength. If you are comfortable with frequency, use P equal to NH nu. And for P, substitute 4 kilowatt or 4000 watt. And for N, you substitute 10 power 20 Planck's constant, you know. Find out the frequency. Or if you're comfortable with wavelength, you can use P equal to NHC by lambda. You know the value of P is 4000 watts. N is 10 power 20. H value, C value, you know. Find the value of lambda. With the help of frequency or lambda, check. If, for example, if frequency is a 10 power 20 hertz, let's say, it might be gamma rays. If lambda is 720 nanometers, so 720 to 10 power minus 9 meters, then it might be visible light, right? So you should be knowing the electromagnetic spectrum, the frequency, wavelength belongs to which domain of the spectrum. You should be knowing this. That would be question number 110. The resistance of a discharge tube. Okay, discharge tube is the tube used for photoelectric experiment ka setup. If you remember a quartz tube, a glass window, and emitter collector, etc. That is a discharge tube. The discharge tube resistance is non-ohmic. Okay, the resistance of a discharge tube is a non-ohmic. We cannot express it in terms of V by I. Okay, so that R is a non-ohmic. Sometimes we say it has a negative resistance also. So it is a non-ohmic. So we will not make any attempt to express it in V by I kind of a concept, because uh, uh, through whichever resistor current flows, right? For that, resistance is defined and it's ohmic. But for a discharge tube, which has a emitter plate and a collector plate, there is nothing in between. There's only electron which is moving. Okay. So I will not be able to define the resistance of this. I can't use V by I to define it. So it is non is what I can. That is question number 111. Now, question number 112. An electron is accelerated through a potential difference of V volt. What is speed of electrons? Well, this is energy conservation. Half mv square is equal to charge Q. Where Q for electron is E into accelerating potential EV. This is the potential energy. This is the kinetic energy. So V will be square root of 2 EV by M. So 112 goes with B. Now, the next question is straight away from NCRT. Few research papers say it is 10 power minus 16 and older editions say of NCRT 10 power minus 10. So we go with the latest edition for this. It's a theory question. You cannot deduce this or derive this from a previous experience. Then a moving electron has a numerical relation lambda equal to h. Lambda here is de Broglie. So wavelength. So lambda is equal to h by p, but they have told that lambda is equal to h itself. So h cancel on both sides. I get p is equal to 1. What is p for electron? Momentum of electron. MeVe equal to 1. So either Me equal to 1 by Ve or Ve equal to 1 by Me, isn't it? So either ME equal to 1 by VE or VE equal to 1 by ME. So C satisfies it. So hence 114 goes with C. Question number 115. In 115, UV radiations ka energy is given. Work function is also given. They're asking kinetic energy. Well, it is expressed in joules. The given data is in form of EV. So first let us make use of EV form. Kinetic energy is incident energy 6.2 minus work function 4.2. That would give you 2 EV. Now convert 2 EV to joules. Simple. Multiply it with 1.6 into 10 power minus 19. So it should be 3.2 into 10 power minus 19, which is option C. Now, question number 116. A light of wavelength 300 nanometer falls on a photoelectric emitter. Good. The next one is light of wavelength 600 nanometer is sufficient for liberating photoelectron for some other surface. What is the ratio of the work function? We know that threshold energy is directly proportional to threshold frequency and inversely proportional to threshold wavelength, right? So phi 1 by phi 2 is lambda 2 by lambda 1. Lambda 2 is 600, lambda 1 is 300, 600 by 300 is 2. Hence it should be 2 is to 1. If you go by elimination, you can eliminate also. How come? Lesser the wavelength, more the threshold energy. So if I take the ratios of first to second, I should get a number greater than 1. So I can eliminate A and D straight away because this ratio gives me less than 1 numbers. Either it is B or it is C. I can eliminate C also, thinking like they are inversely proportional. So when I play with the numbers 300 and 600, there is no way I can get 4 somehow. So I can eliminate that. I can safely choose option B as the answer. Now, going to question number 117, a conceptual question. Energy of a photon is inversely proportional to, we know that E equal to hc by lambda. So, energy is inversely proportional to lambda, wavelength, right? So, that is the option. What about wave number? There's no need to get confused about wave number. Wave number is simply 2 pi by lambda. Okay, energy is not inversely proportional to 2 pi by lambda. It is directly proportional to the wave number. This question can give you multiple conceptual advantage, right? Energy of a photon is not inversely proportional to wave number. It's directly proportional to wave number. It is inversely proportional to wavelength and directly proportional to frequency. Okay, so that is question number 117. If you want more explanation, I can say lambda bar is 2 pi by lambda. Okay? Something like that would be the wave number. Now, question number 118. An atom of mass m, which is in the state of rest, emits a photon of wavelength lambda. As a result, the atom will deflect with the kinetic energy equal to two concepts involved here. One is momentum conservation, one is energy, right? So atom initially was at rest. So when it emits a photon of momentum p, it should repel back with momentum p. Reason, momentum is a vector quantity. If initial momentum is zero, final momentum should also be zero. So momentum of light should be equal and opposite to momentum of photon. What is the momentum of light emitted? We know that lambda equal to h by p or p equal to h by lambda. I can apply these equations for light also. So if I know the photon's wavelength, I know its momentum, which is h by lambda. So what is the momentum of the photon? Momentum of photon is h by lambda in this direction. So what should be momentum of the atom? Momentum of atom also has to be h by lambda in the backward direction. What would happen if I know the momentum? I need the kinetic energy, right? Here is where concepts mingle. We know kinetic energy is p square by 2m. And if I know the momentum is h by lambda, the whole square by 2m. The only option that is matching over here would be option B, which has a 2 in its denominator and squares on h and lambda. Right. So 118 is a combination of momentum conservation and modern physics. If light carries a momentum of p forward, atoms should recoil with the same momentum backward. P equal to h by lambda. Okay. And with the momentum p, how can I get kinetic energy? Kinetic energy is p square by 2m. That would be question number 118. Now, question number 119. What is the momentum of a photon of energy 1 MeV? 1 mega electron volt. Energy is 1 mega electron volt or 10 power 6 into 1.6 into 10 power minus 19 joules. Why did I convert? Because they have asked in SI units. If I know energy, how will I find momentum? Momentum is nothing but energy by speed of light, E equal to PC. So P equal to E by C, you divide this number by 3 into 10 power 8 and you're done. You'll get the answer. That would be question number 119. Now, question number 120 is conceptual. Stopping potential required to reduce the photoelectric current. Okay. What is it proportional to? We know that stopping potential is directly proportional to the frequency or inversely proportional to lambda. Which of them says this? Directly proportional to the frequency of incident radiation. Shabash. So I got option C here, right? And does it increase uniformly with wavelength? No, because wavelength and stopping potential are inversely proportional. So B can't be there. Decreases uniformly with frequency? No. Frequency and stopping potential are directly proportional. So it doesn't decrease or something. Is it directly proportional to the wavelength? It's not directly proportional also. It is inversely proportional. So 120 can be addressed by the basic knowledge that stopping potential depends directly on the frequency and inversely on uh, the wave. Okay, that would be question 1 to 3. Now, question number 121. An alpha particle and a proton are accelerated from rest by a potential difference 100 volts. After this, the de Broglie wavelengths are lambda alpha and lambda p. What is the ratio of lambda alpha or lambda p to lambda alpha? Right. So, which form of de Broglie, which avatar of de Broglie equation will we use? Lambda is equal to h by square root of 2mqv, right? When I divide, okay, both of them have same V, but both of them have different masses and different charges. So lambda P by lambda alpha is equal to, okay, root of mass of alpha into charge of alpha by mass of proton into charge of proton. How did I say this? Because look at the relationship. Lambda is inversely proportional to the square root of Qm. Okay, with this, what can we solve? Well, um, what is mass of alpha particle? 4 times mass of a proton. What is charge on alpha particle? 2 times charge on a proton. So we have MPs and QPs dissolving. Okay, around I get root of 8. Okay, root 8. Root 8 is around 2 root 2. 2 root 2 is around 2.8-ish. So 2.8's nearest integer. 2.8's nearest integer is 3. So I'll go with 121 as 3. Interesting. You are required to use maths as well as approximate over here. So 121 will goes with 3 as you get root 8. Root 8 is 2 root 2. 2 root 2 is 2.8 and nearest is 3. Question number 122. In a historical so and so. Okay. Well, the whole question is about you finding relationship between lambda and V. How do I get that? Einstein's photoelectric equation again. Hc by lambda is equal to phi plus EV naught. I will apply this equation once for this set of data, and I will apply the same equation once for the second set of data, where lambda 1 would be 0.3 micrometers and uh, V naught would be 2. For second time, lambda would be zero point 0.4 and V naught would be 1. So I will have two equations, and from the two equations, I will eliminate phi and get the value of h. The whole question is here you should not assume that you know h. You are actually measuring Planck's constant. You can say that you don't know Planck's constant. You're the first one to measure it. How do you measure it? You apply the equation 2 times for these two sets of data and then subtract the equations. You will get only h unknown, c is known, the lambdas will be known, phi is eliminated, e value you know, and v naught's values also you know. From that you can get the value of h. That would be the approach for 122. Laborious. Only if you're confident that you will get the correct answer, you can go for it, right? And do not assume that you will get this as the correct answer. No, that might be a trap set by the examiner. Only that value which you get by subtracting and solving, that will be the correct answer for this. Though the exact value of Planck's constant is 6.6 to 10 power minus 34, you should not take this because you have to determine it from whatever values you have measured from the experiment. So it might happen that the answer is D, B, or A also. So it is entirely mathematical. Apply the equation 2 times, subtract, and get the value of h in terms of c's, lambdas, v naughts, and e. E is given as 1.6 into 10 power minus 9. This is question number 122. And for question number 123, stopping potential and frequency graph is given. How do I relate them? H nu is equal to phi plus E V naught. Now, h nu is in x-axis. So I can rewrite this as V naught is equal to h by E nu minus phi by E. What is the use? V naught is plotted in y. Nu is nothing but h, right? Y is equal to mx plus c form. The slope of the graph, this theta. So tan theta is always h by e. Y, compare it with y equal to mx plus c. The coefficient of x is h by e. H by e should be tan theta. And what is the intercept? Intercept is phi by e. So what would be intercept giving you on the potential axis? It would be giving you phi. Phi is nothing but work function. Only if you can rearrange and compare this with the standard line equation y equal to mx plus c, then you will be arriving at the right answer. 123 goes with A. Now, question number 124. The stopping potential in an experiment is 1.5 volt. What is the maximum kinetic energy? Direct relationship exists. Half mv square is equal to EV, right? E is 1.6 to 10 power minus 19, and V is 1.5 given, and mass of electron is, of course, 1.6 into, 9.1 into 10 power minus 31, right? That is mass of electron. From there, you can get the value of V. All right. Or since they are just asking what is, they are not asking speed, they're asking half mv square itself. So you simply multiply 1.5 with this E, which is 1.6 into 10 power minus 19, and you will have the answer. What is 1.5 into 1.6? You try to approximate it. 1.5 into 1.6. Okay. It should be lesser than 3. So one approximation can suggest it should be option C. Okay, 1.5 to 1.6, slightly lesser than 3. So the one slightly less than 3 is 2.4. So I'll go with option C. Next one is a doctor kind of a question, a broken ligament, which some of you will be dealing with perhaps in your medical career. It is being welded by using zero point 0.5 watt laser operating at 632 nanometers. So, number of photons. Let us first find what is the number of photons in first pulse. In the first pulse, we can use P is equal to NHC by lambda. Power is given as zero point 0.5. H value, Planck's constant we know. C is speed of light. Lambda in SI you have to use 632 into 10 power minus 9. Solving, you get a number of photons in first pulse. But they're asking number of photons in 5 pulses. So whatever number you find out here, N, do 5 times that, and that would be the answer. That is the answer to question number 125. Now, question number 126. You're using light of wavelength 1400 nanometer. I will simply find the energy equivalent of this. Okay. So how much energy this will carry? That I will use. E is equal to 12,400 by lambda in angstroms. Angstroms for 1400. How much it would be in angstroms? That would be 14,000. So if I do this calculation, I will get some energy value. Okay. How much EVs I will get? Two zeros I can cancel. 124 by 140 around. E is equal to 12,400 by lambda in angstroms. Okay. How are the 4 options related to this? Right. Well, only that light which has around the same EV value will work for this. That's how you can establish question number 126. There is something ambiguous about it also, but you can go with this. First, calculate the E equal to HC by lambda. From there, you can get the what is the EVs you require for band gap, and then you can find the answer. It is from semiconductors, actually, photodiode. Now, question number 127. The photoelectric effect establishes that. What is the conclusion? It has nothing to do with waves theory. I can eliminate B, C, D totally because all of them deals with longitudinal, transverse and stuff. Only A deals with quanta. So photoelectric effect establishes that for light interacts with matter in terms of pushes or energy packets called quanta. So 127 goes with A. These are the quick approaches to the questions of modern physics or dual nature of radiation and matter in your NEET test 5. Most of them can be solved through elimination. Some of them have long mathematical calculation. So if you increase your calculation speed, good for you. Take care till next time. We'll meet with the future discussions. Keep having fun with physics. All the very best.